Right, Assalamualaikum and a very good day to everyone. So we're going to continue the lecture for single degree of freedom system, and now we're going to focus on free vibration of undamped torsional system. Right, so in our previous session we have looked on translational system, and now we're going to look on torsional system. So we know that from Newton's second law, for translational system, sigma f is equals to mx double dot. But for torsional system, okay, it will become sigma moment equals to j theta double dot. So you can see that the difference here. Okay, F force in torsional it become moment, and if we use mass in translational system, it has become J, or second polar moment of inertia. And for translational system we use X to represent the coordinate, but for torsional we use theta. Okay, so X double dot in translational, and for torsional we use theta double dot. Okay, right, so in order for you to find the moment, these are some of the equation that you can use. Okay, whereby I is the polar moment of inertia, or sometimes we can represent it as J naught. Okay, so this is the representation of torsional system. Okay, we don't see any spring there. Okay, and we see a disc, we see a shaft, we see a disc. Okay, we don't see mass, we don't see spring coefficient. Okay, and polar moment of inertia also we can use this equation. Okay, I naught is equals to pi d to the power of 4 over 32, and the torsional spring constant. Okay, because sometimes the question don't give you directly. Okay, it doesn't give kt is equals to something. No, sometimes it give you what is the value of g, what is the value of I, what is the value of L, the length, so you can find what is the torsional spring constant. Okay, so we know that I is equals to pi d over 432, so kt is equals to g I naught over L, so g over L multiply with pi d to the power of 4 over 32. Okay, so it becomes like this. Okay, and then the equation of motion, we know that from translational system, free undamped translational system. Okay, the equation of motion is mx double dot plus kx equals to 0. So for torsional system, m is represented by j dot, x double dot is theta double dot, k is represented by kt or torsional stiffness, and x is represented by theta. Okay, and in here for translational we use F, and for torsional we use M. Okay, external moment, but in this case because we're considering free undamped vibration torsional system, so it doesn't have any M value. And for translational system, to determine the omega n natural frequency, it is actually square root k over m. But for torsional system, it is kt, torsional spring stiffness, over j naught, j dot. Okay, sorry, j naught. So meaning that for torsional system, omega n is equal to square root kt over j dot, j naught. Okay, so this is some of the equation that you can also use if the question didn't give you directly what is the j naught value and so on. Right, And in terms of response, so if you can still remember from our previous lecture, okay, this is the response for translational system. But now since we are considering rotational system, so x has become theta, time remains time, is equals to a1 remains cos omega n t plus a2 sine omega n t. So this is for torsional, this is for torsional, and this is for translational. Okay, so this is the difference in terms of response between those two. And same goes to the initial condition. Previously we used x naught, x dot naught, but for torsional we're going to use theta naught, or it's actually theta when t equals to zero, and theta dot naught, which is actually the value of theta dot when t equals to 0, and the rest is the same. Okay, so now by using this initial condition on your own, try to determine what is the a1 and a2 value, and in the end you will get a1 equals to theta naught, and a2 is theta dot naught over omega n. Okay, so this is the difference between torsional and translational system. Alright, thank you very much, and on our next session we're going to look on some example on how do we solve the question. Thank you.